Thank you so much. I'm so glad to be here and happier that you're here with me. So we are now connected. This is actually a talk kind of about connections, relationships. So welcome. I work for NVIDIA. I'm on the Rapids team. We make data science go faster is kind of our short pitch. And this is part of our effort. We've been working with the NetworkX team to make NetworkX faster with our backend. And there's lots of potential here. The agenda is kind of like simple, like the take-home messages of graphs are everywhere, I claim anyway, and it's a question of how well do you know your data and how well, are you extracting all the value from the data as you can? Secondly, is NetworkX is a great library. If you're doing graphing, like you're probably using NetworkX today or have tried to use it and found it was slow. So NetworkX with backends is such a positive story. It makes NetworkX better. It keeps it the same, but gives it like new superpowers, new abilities. And it gives you the flexibility to kind of evolve your workflow and scale with your data. And, our pitch is, hey, like if you want it to go really fast, run it on your, NVIDIA GPUs with our new backend. So question of the audience, who here works with the data? All right, everybody's active. I love an engaged audience. Like we are at a conference with data in the name. So who works with graph data? Wow, it's actually more than I expected. So who doesn't know how to answer that because I haven't explained what graph data is? But not nice. Well, as like the takeaway message, I say graphs are everywhere. So I think graphs are kind of everywhere. It's used in virtually like all fields of science and engineering and even in businesses. And this is because like as the world is connected, so too is data. This is like, I see so many graphs in this image of like, yeah, it's a highway. We have roads on a traffic network. There are people on the roads. They're going from a destination to from a to somewhere. So it captures action. Like it captures like they're doing something. They're all like shared on the same road or they're part of a family. And yeah, maybe it's I am in a bubble because I see graphs everywhere. My news feed and my social media, first, social media is a giant graph. It's a network, and I get my personalized feed based on what I like, based on what people around me like. And this is like one application of graph analytics, of personalized recommendations. And so in my news feed, I am seeing, probably just me, that graphs are having kind of a moment. And if it's not we're this now, like you might be soon, or if you're in an organization, we're like, hey, let's figure out like our data strategy for graphs. Like I said, like graph problems have always been there, but there's so many kind of new use cases coming out. I see like the research community is really into graph neural networks. Sometimes though, personalized PageRank is all you need, and you should start with traditional graph analytics. GraphRag for large language models is a way to help it kind of hallucinate less and just give better answers. So this, like using that with the opening keynote from Sophia. Knowledge graphs and property graphs are how I think organizations will try to kind of manage and think about their data. And data exists, it's super complicated. It's in different silos. And like, well, what are the relationships between the data and the different silos? Naturally, traditional graph analytics and graph queries, like who was Amy's, second cousin who has the red car? That's kind of the traditional graph query. I don't know where that example came from. And we're just like, we need to store the data, persist it, and use graph databases. So like this image is more of a normal. We have nodes and edges. So the big picture, I could actually stay on this slide, just all talk the rest of the 20 minutes and just talk the whole time, but I won't. Like I said, like data is actually really messy, really complicated, and it can come from anywhere, and it can be small, it can be big, it can be like you need to do joins, you need to parse these log files or CSV files, or you're a scientist, you have floppy disks. And maybe have some graph problem or application, and like yeah, like we have a library, NetworkX, to do traditional graph analytics, but this is often not like your end-to-end workflow. It's defined by like your data and like what you're trying to do, and hopefully you're trying to improve the world some way. This is a, like we are a connected species with lots of connections, and so I think like the pitch is that if you have something that's kind of like fits in this mold, that NetworkX should be part of your story. It should be part of your technology stack. In particular, NetworkX with backends it's not the same NetworkX as it was like 3 years ago. It has new capabilities, and like it's very flexible. You can like make your own backend. It's now scalable, and it's still like the same NetworkX that's easy to use. So a short just kind of pitch of like, well, why do I say NetworkX is so great? It's because a lot of people use it. On PyPI stats, like it has 69 million downloads from the last month alone from PyPI. So I was tempted to say the most popular graph library in Python, but I don't think like, if it's the most popular library in Python for graphs, it's probably for any language. So it's the API of users. And it's been refined and like contributed to over the last like 2 decades or so by the community. And so it's permissively licensed, which makes it easy to use. Lots of stars, lots and lots of contributors throughout the year, and these are often like a graph researcher, contributes this, or a user says, "Hey, I need something," and we have added like dispatching to like several hundred of the functions. This was no small feat to be able to use backends, and if you want to learn, like there are ample resources. So documentations, examples, Stack Overflow blogs, just like, yeah, it is like the on-ramp for like learning how to use NetworkX is probably where you should start for graphs. And then you can actually continue further and like make it scale go faster. So it's mature and battle tested and bug vetted, and with backends it's better. So yeah, it's always great. I've been saying this a lot. With new backends in dispatching, we can just add this to your workflow either kind of explicitly, where you say like use this backend, or automatically. And this is an example of, I'm just going to make a basic toy graph with a few edges, add edge with a weight, AB, BD, AC, CD, and find me the shortest path. This is one simple graph algorithm that you might want to do. Like I'm trying to get between A and D, and it says, oh, well, the fastest path is from A to B to D, because that adds to 6, A to C to D adds to 7. If you wanted to use cugraph, which for this data is kind of silly, it's really small, but you could just say backend equals cugraph. Or we could set the configuration like directly via code or with an environment variable to automatically run with the NX cugraph backend. And so in this workflow, we still make a NetworkX graph, and when we use this backend, we automatically we convert it to the GPU version of it. Like we copy it to the GPU, and in recent versions of NetworkX, we actually save this conversion. So if you do more algorithms after this that use the GPU version, like you don't need to pay that conversion cost every time. So we've been working on this for 2 years now, and it's been sort of in an experimental, things may change sort of state, but now it's finally like, yeah, we like it. We like where it is. We're going to keep it. So it's no longer experimental. The documentation is better. We're about to do a release 3.4, and although it's been here the last like 2 years or so, the latest is recommended, just for like introspection and just yeah, like it has been changing. Yeah, like why do we even want backends? And I saw several hands up. What is that? Like, do you have graph data? And have you ever tried to use NetworkX? And have you ever tried to use it on larger data? If so, a story I've heard a lot of times is that like, hey, we love NetworkX, but it just gets really slow. Like it is too slow for our data. And so like, it's hard to recommend it because blah, blah, blah. But one feature, like new ability that backends give us, like it allows us to have binary data structures with native performance. And so, you know, you don't think of NetworkX as being like the fastest library, but NVIDIA likes to make things fast on GPUs. But if you are like actually doing like lots of mutations or need to store really weird things, the NetworkX data structure of a dict of dicts for edge data is actually extremely flexible and it's extremely dynamic. Like you can add and delete and you can change it. And like there are people today, like they use it for the data structure because it's actually pretty nice, but it's not the fastest. So I would love to spend a lot of time just digging into benchmarking, saying, hey, we make this one go faster. This is like this many like X times faster because, you know, people at NVIDIA love to make things fast because we like to show off our hardware. But I'll just kind of give a hand wave, like generally, like if you know, like if you try a problem and it's slow, like a common, it's to see things that take hours to days with NetworkX on larger data. To run it in seconds or maybe sometimes even minutes, which is still must be like doing a lot of work if it takes minutes on a GPU. We are working on documentation. There's a link at the bottom to a document to show some of the examples, just to so like to help answer like, well, how much of a speed up should I expect for like my graph problem, the thing I'm trying to ask? Because it's very data dependent, not just the size, but also like how the connectivity is in the data. And yeah, this is a very valid question of like, well, how much speed up do I want? Well, but if you want it to be faster, you could always write your own thing, your own specialized data structure. So this is my most important slide. Planned water break. So what do you see here? I'll tell you what I see. I see graphs. I see graphs everywhere. Have I told you this? So naturally, it's a sequence of the first 9 natural numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9. And I love natural numbers. Simple thing I just think of like, oh, like what are the prime factors? You know, and you know, 2 has a multiplicity of like, or 4, 2 times 2, so there's 2 of the 2's. Yeah, so I see, it's not just one graph. I see lots of graphs here. I don't actually include like the prime factors for 1. That is way too many lines, and it would become like a hairball. So another way I like to view graphs is as an adjacency matrix. And so here I'm looking at the coprimes, like is 2 coprime with 3? Like is the greatest common denominator 1? And an adjacency matrix avoids the view of the hairball you would have of the graph, like if we try to like draw all those lines, and lets us like show, you know, these are relationships between 2 of the nodes. So it doesn't matter what a coprime is. We could come up with all kinds of relationships between natural numbers. But let's make a few observations that this is a square matrix because like the node sets for the rows and the node set columns are the same. It's an undirected graph. It doesn't matter which order things in, like 2 is coprime with 3, 3 is coprime with 2. 1 and 1 is the only self edge, like it's the only one that like the edge goes in on itself because 1 is the only number that's coprime with itself. And missing data, like zeros, are usually not shown. So a sparse problem really is like it's equivalent to a graph problem. If you have a graph data or sparse data, like it's equivalent. And so matrices, like if you just give me a matrix, it's like, aha, I see a graph. But if you say, oh, Erik, my matrix isn't square. My matrix, my array, is rectangular. Is this a graph? Is this an adjacency matrix for a graph in particular? Well, first off, like it doesn't matter if it's dense. Like dense, you can be like, everybody can be connected to everybody. And if we can do data science, we can regularize our matrix in some way, possibly to like, oh, let's just like throw out the small numbers. So we can make a dense matrix more sparse and make it more like a graph. But I still haven't answered, is this an adjacency matrix? Sure, why not? Let's make it a, this is a particular view for a bipartite graph where we have like two different node sets. And so here we have the entities on the left of like 1, 2, 3, 4, 5. These are like the natural numbers before. But on the top, we have like A, B, C. I don't know what those are. Those are just sets. And so we have really some relationship between one node set, like the 1 to 5, and the other node set, ABC. And this is actually extremely common. And a lot of the data you'll see like actually kind of comes in this form, or even like a multipartite form, not just like two sets. And an example is that, well, maybe one set is like users, and another set is products, or these are like the pages they're visiting, and like super common. And so we can actually take this form of the like rectangular matrix and say, well, actually, let's reconstruct our adjacency matrix like I was talking about before. And so this way is square. And what was dense is now like, well, we have a bunch of sparse data because A doesn't connect to B or C. It only connects to the other things. But Erik, you say again, my data doesn't look like this. Well, what does your data look like? I'm going to guess. Most data in the world, like just as a natural scientific approach, probably looks like a data frame in some way. So we have like maybe observations and then stuff about the observations along the columns. And like my head is like, oh, this is, not that it's surprising that I see graphs in here, but my head explodes because I see so many relationships in here. Like just give me a data frame and I'm like, oh my God, like what do you want me to do with it? So yeah, and so just generically, I could say that like a relationship with data frames is like, hey, is this row similar to that row? And similar here can kind of mean virtually anything. Like even like the rectangular matrix before, I could say, oh, like is this row correlated with that row? Like that's a similarity. So graph thinking really is relationship thinking. And this is often done in the way of, hey, like source relation object. SRO is what you'll see sometimes. And properties may be adverbs or adjectives. You can have properties on the graph, or properties on the nodes, properties on the edges. But properties can also be nouns. I hope you see some graphs in here. I do. It's not like, oftentimes like your data frame, it's not obvious like, well, actually like what is the source and the destination? And so a very useful form to like, get things in a good shape is to actually have new columns that you say, hey, this is where an edge begins, and this is where like the target of the edge. And we call this like the source and the target to indicate the edge boundaries. And the rest of the columns can just be some relationship between these things. And so data in the real world can be large and messy. And this is what I keep saying too, that hey, we have transaction data, log data. If you have data silos and then you need to do some joins, like join data can get very, very big as well. And it's really common, actually, to have millions or billions of edges. So how large do you think graphs are that the CIA use? I have no idea, so don't ask me. But it's really fun to just wonder this out loud in a recorded talk. Like, do you think it's a trillion edge? Trillions, plural? I think I'd like to find out, but I don't know. Yeah, like it's like human scale, the internet scale of things. Things can get big. So NetworkX loves data frames. And the common workflow is to, hey, let's start, I'm going to walk through the code of like, let's just use pandas and NetworkX together, read a data frame from this URL. It's got 16.5 million edges. It's directed. It's really not that big. From pandas edge list, we say which columns to use. And we run between centrality. This is like we ran shortest paths before. Between centrality runs lots of shortest paths to figure out like, well, which nodes are in the most shortest paths between different things. And with NetworkX, this runs in 7 minutes, 44 seconds. I told you I wasn't going to show too many benchmarks. This is not quite a benchmark. I didn't tell you the hardware. But in XQgraph, this now runs in 20 seconds. So this is real pain. Like if you're waiting, like you're going to go get a cup of coffee, or you're just going to sit there at your computer. It's a difference whether you sit or walk. And we, that 20 seconds, by the way, includes the conversion of moving the data onto the GPU. And yeah, we only pay that conversion once, but we still have to pay it. So let's try to optimize this a little more. Optimization 1 is like, let's try to not create a NetworkX graph. We can do this by saying backend equals cudf in the from pandas edge list. Coming soon, we could actually like do this zero code change. And now all of a sudden, we avoid, end to end, this would be a lot faster, but we can do even better. Let's keep the data like on the GPU. Let's move it there as soon as possible. So let's use cudf.pandas to create the data frame and use cudf.pandas. It's already on the GPU to create our next cudf graph. And all of a sudden, I bet this would be a lot faster. Again, there's no time to actually go into the timing of things, but cugraph and cudf are part of like really big stacks and a lot of ecosystems of like, hey, we want to accelerate data science in Rapids. cugraph, like without the NX, it's part of a library that can scale to multi-GPU and like it can run PageRank. They did an experiment to run PageRank on a trillion edge graph in 19.3 seconds, which is mind-blowing to me. So yeah, Rapids is really swell. But I hear backends are, you can do fun things with backends. They can do more. So what if we just treated data frames as a graph? Okay, well, let's give it a try. So as an experiment, we made a new backend in Pandas. And here in the thing, the code on the right is a lot kind of shorter. Now we read CSV, and I set, like there's a new .nx accessor GDF nx properties, because they have to tell it like how to interpret this data frame as a graph. This is my source, this is my target destination, it's in the nice COO format. And you run between centrality on this, and we configured it to run with cugraph, so it'll go straight from this data frame to an X cugraph. It's not yet released, we're gonna plan to release it soon. So yeah, NetworkX today has 5-ish backends. There are more. So we do, I've talked a lot about the GPU acceleration of our backends, but there's so many more exciting things going on. And it's actually like it's all tells a good story. Like our stories are one and the same of working together. And OrangoDB has joined in the fun of let's be the first graph database that makes a backend for NetworkX. And people on NetworkX, I hear, have been kind of asking, like wanting a better way for graph persistence, and ArangoDB can do this. And they're working closely with us so they can go like straight from ArangoDB to cugraph. In X parallel accelerates just regular NetworkX, so it could still have the flexible data model, but it runs things in parallel with a job lib. I mentioned NX Pandas uses data frames as graphs, graph loss algorithms. Clearly, the naming convention is not quite right yet, but it was actually the very first NetworkX backend. It blazed the path. And it's backed by a graph loss. And, I think there may be, hint, hint, wink, wink, proprietary, private, closed source backends definitely exist. So yeah, I think this is great, and more should exist, I hope. You can install these today. I just want to say merci beaucoup.
Thank you very much for the presentation. If you have any questions, please raise your hand.
Hello, Erik. Thank you for the presentation. I just have two questions. One is like, I can assume that it is an extension of QGraph, right? The NetworkX can be considered as extension of QGraph. So like, how compatible it is actually with NetworkX? Like, are all the parameters in the NetworkX algorithms are supported there? Or if some parameters are not supported, what happens?
I did not plant you in the audience, but that is an excellent question. I should have mentioned that, like, one, we do run the NetworkX test. Like, we have it so that the backend. So as a user, you can be trustworthy. Like, hey, this backend should give the right answer. We also update the doc strings of these backends are available, and it has these additional parameters. Or a backend might say, hey, I don't support this, that, or the other. And in that case, a backend is supposed to, one, document it in that doc string, so the user can just see straight up in the NetworkX documentation. And two, there's like a concept of like a should run or can run. It should just say, hey, actually, I can't run with this. Like, you're doing something that I just don't support yet, because this is like, we didn't implement all of NetworkX. Like, it was 1,000 functions and even like dispatching. So like, yeah, we're not gonna say day one, we do everything, but we do a lot actually. And so if there's something missing, please, like, we're all working the hardest we can, but please say, hey, we would like this. We've gotten requests for like graph isomorphisms and other ones.
Perfect. Actually, what I asked, like, I like QDF in CUDA data frame. Whenever there is something not supported, it fallbacks to pandas, right?
Oh, yeah.
So I thought of if something happens here as well, that if something is not supported by QGraph, is it automatically falling back to NetworkX or something? If that
Oh, boy. Well, this is planned, like the general availability for an X2 graph is planned for like ish soon. And this is the work I've done the last like couple weeks, last month, is to make it so that we do have like a fully compatible graph that acts a lot more like cudf.pandas, where, hey, we'll do things on the GPU where possible, or like we'll just fall back to NetworkX. And if you start with like a NetworkX graph itself, and the data is already there as a NetworkX graph, like using the cache gives you that story already, but we want to sometimes avoid making the NetworkX graph directly, and it's like, let's go straight to GPU. But from there, fall back to NetworkX if necessary. Again, I didn't plant you in the audience, but that is an excellent question. So yes.
Thanks so much.
And also highlights cudf.pandas. Good.
Hello, thanks. Great presentation. Just a quick question on to implement custom function. Is there some thing you can do on Python, or you need to go lower level? What's the official way? Thanks.
To implement a custom function, do you want to like say, hey, this is a new thing that backends can do, or like, this is Python, we can do anything?
Yeah, like you can do in Python, but like if you want to implement to run it on the GPUs, like because you said there are many functions, some are not implemented. If you want to do it yourself, if someone wants to do it themselves, like, is there like a way to expand the backend to create extensions for the backend?
Actually, so like if you wanted to say, hey, like add these things, like implemented this for an execute graph. You don't have it yet, but I just want to maintain it myself. The way to do that today, I would probably say, is like make a new backend, and
Okay.
like this probably makes sense as
So
a,
there is no.
if it's a new package. And I want to make like the backend to backend this story a bit better too. It's one of our main to-dos. But yeah, like MongoDB is able to work around this. NetworkX Pandas is able to do the same thing.
Thank you very much. I think we are running out of time. There is a break now. So if you have additional questions, please feel free to reach Erik after or during the break. Thank you very much.
Thank you.